We'll welcome you nonetheless. We do provide umbrellas, yeah, with a nice skyline on them and everything. So please come by anyway. So I want to talk about genetically modified galaxies. This is something that, for those of you who were here at the NICE workshop last year, I talked a bit about this technique for the first time. But what we've been doing in the meantime is actually applying it to do some science. So that's what I want to talk about. And in particular, I want to talk about some work we've been doing looking at quenching using this technique. And I'll try and give you a very fast review of what the technique is as well. Before I move on, I just want to call out that there are a large number of collaborators on this work. And in particular, I wanted to draw your attention to Michael Tremmel, who's going to be giving his own talk later on. But he's been working very hard on the black hole physics implementation inside the Changa simulation code, which is what we've been using here. And also Nina Roth, who was a postdoc with us at UCL, and worked very hard on the implementation of the genetic modification idea. So a lot of this work owes to their efforts. So since I'm the very first talk in the quenching session, I thought it was worth just making sure that everyone's on the same page. You know, quenching is clearly a super important process to understand if you want to convince yourself that lambda CDM really works to explain galaxy formation. The simple fact is that there are very clearly physics to be understood in how galaxies go from being star-forming and having a disky morphology to being red and dead and having some kind of elliptical morphology. And that physics is clearly far from trivial. There's an awful lot of different things going on. One thing you can look at is, say, have a look at the fraction of galaxies that have stopped forming stars as a function of both mass here on the x-axis and overdensity here on the y-axis. So this is from the seminal study in 2010 of SDSS galaxies. And something that you find is that galaxies quenching correlates very strongly with both of these things. But it's not like a one-to-one relationship. It's not like you move from one place in this plane to another place in this plane and either you're star-forming or you're quenched. You know, there are large areas of this plane where there are galaxies that are both star-forming and other galaxies that are quenched. So clearly, there are a lot of variables at play. It's not just a straightforward question of environment and or mass. There are other variables at play here. And that's one of the reasons why we wanted to apply our technique to this question, because one of the strengths of what we're doing with these genetically modified galaxies is we can fix the mass of a galaxy and fix the cosmological environment of a galaxy, but then tinker about with its cosmological merger history. So I'll show you that in a moment, but that's kind of the motivation for why we wanted to approach this using a new simulation technique. Now, it's been known for a long time that AGN clearly have an important role to play in controlling the bright end of the galaxy population and then presumably controlling this whole process of quenching. Here's just one example of the many, many works that have been done on this. This is from the Eagle simulation from the Leiden group and other groups in Europe. Having a look at the luminosity function at low redshift and matching it with some large volume simulations. And the point is that you really need the active galactic nuclei. You need the black hole feedback to get anywhere close to matching this bright end slope of the galaxy luminosity function. If you switch off the AGN, and I've just overplotted this from another plot, if you switch off those AGN, you just consistently overproduce bright galaxies. So you really do need some kind of energetic feedback at the bright end to work out what's going on. But on the other hand, if AGN and quenching were Facebook friends, then they would have a relationship status of it's complicated, I think, because it's not a straightforward question of, okay, an AGN switches on and blasts a galaxy, and that's the end of the star formation and the galaxy is dead. There's something much more complicated going on, and there are many, many observations showing this. I'm just giving you one example here where you can find galaxies which have very rapid outflows driven by some central AGN. So this thing has outflows going at about 1,000 kilometers per second. But at the same time, if you can see down here, This is the N2H alpha index, and there's clearly star formation going on in this galaxy as well. Not that far away from the AGN, a few kiloparsecs away from the AGN. So a simple picture in which AGN just blast their host galaxy and switch off the star formation is not going to cut it. And finally, before moving on a bit, I want to point out that one of the most remarkable observational developments of recent years is just seeing how this relationship between quenched and unquenched galaxies is built up at very high redshifts. Very rapidly in the early universe, you build up a fraction of quenched galaxies that increases with stellar mass. But even, say, between redshift 2 or so, these blue dots here from candles and 3D HST data, you can get a quarter of all galaxies quenched at stellar masses of 10 to the 11 solar masses or so. So clearly, quenching is not something that takes the entire age of the universe. And in fact, you can go and study individual objects and take a look at various indices which give you direct observational handles on how fast quenching takes place. And the fact is that sometimes things may be able to quench quite slowly, but other times, for a very significant fraction of objects, you can tell just by comparing different star formation indicators that they've quenched very fast. That they have, this is an object here that's been caught in the act in this nice paper, and it's literally just in the process of turning off its star formation. And when you look at these things, they can turn off star formation in a few hundred megayears. So there are processes out there that turn off star formation very, very rapidly. So with all of those things in mind, we set to work using this genetic modification approach. And in short, because I don't have time really to go into the technique this time around, the idea is that you set up Zoom simulations so that you have nice high-resolution cosmological simulations, but you make slight changes from one simulation to another in a very controlled way. So what you have here is 3 different simulations run independently with just very slightly different initial conditions. And these are Zoom regions. That's why you've got these weird potato-shaped blobs at redshift, whatever this is, redshift 50 or so. They're the Zoom regions that we've populated with high-resolution dark matter and gas. And as you go forwards in time, these regions develop in a very similar way, but we've carefully controlled the initial conditions in such a way that we know that they're going to have a slightly different merger history. So in short, this whole idea of genetic modification is to generate very slightly different initial conditions that give rise to different behavior as you go forwards in time. And I'll show you exactly what that behavior is in just a moment. If you take a look at the initial conditions to see, well, just how different are these things, what are we talking about here? We really are talking about very subtle changes. So here's that same potato-shaped Zoom region in the initial conditions at redshift 99. This is just a linear Gaussian random field at redshift 99. And the kind of changes that I'm talking about are barely visible. So if I switch from the original reference run to one where we're going to have an enhanced merger to play with, you can see there's very little difference. I'm just flicking backwards and forwards between them there. There are very, very slight differences. And this is the actual difference field that we've constructed. And again, unfortunately, I don't really have time into exactly how this is constructed. It's done in such a way that you maintain the power spectrum, you maintain the consistency with lambda CDM. It's basically like just having different draws from the lambda CDM Gaussian random field. And for people who like the technical details, this is using something called the Hofmann-Ryback algorithm, which you may have come across if you've looked at papers on things like the constrained local universe simulations, where the idea is to try and match the large-scale structure of the local group. So it's the same kind of mathematics, but we're using it for a different purpose to generate a series of simulations that just differ incrementally, have slight changes in their early time large-scale structure, which then lead to slight changes in the merger history that comes out.
What are the actual constraints that you put in?
So there's basically, to change the merger history, you put in 2 constraints. One fixes the density of the final object. So that basically says I want it to be a certain mass at the final time. And another one changes the density of one of the merging objects so that you can make the infalling substructure form earlier or later. So that's what goes into the constraint.
The merging object by eye or
Can we maybe come to that in the discussion? Because it is a bit of a technical point, but I can explain in the discussion. Okay, so then, of course, you have to run these things. We have three related initial conditions. We run them with the Changa code. I mentioned this earlier on. Michael Tremel's been doing a lot of work in putting a very nice black hole implementation into this. This inherits a lot of the physics from the older gasoline code, and the main difference is the way that it scales to a much larger number of cores using task-based parallelism. But I don't particularly want to focus too much on the details of those simulations. Michael will say a little bit more about how these simulations work in his talk later on. So if we go back to taking a look at what actually happens in these three different cases, so let's run this movie again. You can see at early times, these regions, the three different simulations, evolve in a very similar way. So I've just paused this at about redshift 8. The large-scale structure, by the way, you're looking at gas, and the colors are temperature in this. So the large-scale structure at redshift 8 really looks the same. So you're forming a central galaxy out of the same large-scale filaments, feeding gas in the same way into an object. Then if I carry on running this thing, because of the very slight changes that we've made to that initial density field, the history plays out a little differently. So take a look over on the right there. I've paused it now at about redshift 4. And there's about to be a major merger over on the right. That's going to be about a 2 to 3 merger. So we've genetically engineered that to be as close to a 1-to-1 merger as we could make it. Whereas in the original reference run, it was more like a 1-to-5 merger. So a more moderate merger was taking place. And in the suppressed merger, it's going to be a 1-to-10 merger. The other thing you'll notice about this is that these things are at different places in different stages in falling in. They're the same particles, but in the suppressed case, it's going to fall in later because it's further away than in the enhanced case where it's going to fall in a bit earlier. That's kind of a byproduct of having to maintain the lambda CDM power spectrum. So things become correlated. And if you like, you can add more and more constraints and try and get things to happen exactly the way that you want them. But we've taken the approach here of just saying, well, if we say we want a major merger and the algorithm says, well, that means it happens a bit earlier, well, fine. Okay, we don't mind about that too much. So we just allow that merger to take place a bit earlier. And then if you wait just a small time later, the reference merger takes place. And then after that, the suppressed merger takes place. And like I say, these have very different merger ratios. So if you look at the buildup of mass, this is just looking at the virial mass of this thing over time. This white line here is the reference unmodified simulation, the very first thing that we ran. And one of those constraints is to try and fix its mass at the end of this simulation. We are stopping just momentarily after redshift 2, by the way, partly because the observations are getting very interesting up at high redshift, also partly just because we wanted to get this work out. We're going to look at extending these things to lower redshift soon. In any case, so we fixed this target mass, and then if we plot on where the merger takes place, that's that 1-to-5 merger taking place just after redshift 4 or so. If I now show you what the enhanced run looks like, it has a 2-to-3 merger that takes place a little earlier, but it hits that same target mass by the end of the simulation. And similarly, I can show you the suppressed merger case, where it builds up mass rather slower at early times, and then it has a 1-to-10 merger. And then something a little interesting happens in the suppressed case. You'll notice that there's a rather steep rise in the virial mass that takes place quite quickly after this 1-to-10 merger. And what's going on here is that to make up the final mass, what the algorithm ends up doing is creating a whole series of rapid minor mergers, because otherwise you just can't reach this final target mass of around 10 to the 12 dynamical mass at redshift 2. So as you play around with these things, you do get slight changes in how the structure around your galaxy evolves. But that's okay. I mean, the thing that's really nice about this is if you look at the end of the simulation, in the three different cases, you have large-scale structure in the three cases, which really looks very similar. If you measure the large-scale overdensity, for instance, it's identical between these three cases. So really, as close as you can make it, you've kept the cosmological environment fixed, but changed the merger history of these things. And the effects on the central galaxy are pretty dramatic. So I can just show you, this is at about redshift 2.3, what the central galaxy sitting in the middle of all of that looks like. And this is a run with black hole and supernova feedback. And what you find is in the suppressed merger case, this thing is still merrily forming stars. It has a nice star-forming disk. In the reference case, it's kind of quenched, although if you look closely, there is actually a trace of star formation still going on. And in the case of the enhanced merger, that one-to-one merger, this galaxy has really died. There's really very little star formation going on at all. And just to say, if you switch off the black holes, so we reran these simulations without Michael's implementation of black holes, just with supernova feedback. The way that the galaxy responds to the mergers is much less pronounced. Basically, it's very, very hard to get the galaxy to quench, we find, when we only have supernova feedback in this particular case. So the question comes about, well, what is the black hole actually doing? Why does it differ between the three cases? So let's first of all just take a look quantitatively at what the star formation history looks like. I'm going to show you the specific star formation rate as a function of time in these different simulations. There's roughly where we think the main sequence should lie on this plot. And if you're using something like the UVJ criteria to define what a quenched galaxy is, then the star formation rate has to fall below this threshold to count as quenched in that particular selection. So in the original reference run, what we find is we have a galaxy that is sitting on the main sequence, then it has its merger. The galaxy merger takes place around here, and it momentarily quenches, but it actually rejuvenates again. It bounces back onto the main sequence. And what we find is if we slightly sneakily just run this simulation for a little longer, it carries on going up. So it really does just rejoin the main sequence, this galaxy. When instead we enhance the merger, something quite different happens. First of all, the galaxy merger takes place just a little earlier. And then the moment it takes place, the star formation rate really falls off a cliff over just a couple of hundred mega years. It falls right down, and it stays down. And again, we've just sneakily run these simulations for a little longer, and we find it just carries on sitting on this kind of quench track right here. And finally, if you look at the suppressed case, in fact, the main thing that you do with the merger in that case is, because of this rapid minor merging, is you kind of get a starburst behavior, and then this thing actually ends up oscillating around inside the main sequence if you extend this just a little further, which a number of authors have pointed out is a behavior that you can expect to see in high redshift galaxies. So we really do have quite different behavior just responding to this different merger history. Now, one thing that you can do is say, well, clearly, as I showed you earlier on, the black holes are critical to establishing the quenching. But what's really going on in this case, where the quenching seems to carry on more or less indefinitely, as far as we can see at the moment? And one way to address that question is simply to turn off the black holes. So suppose I turn off black hole accretion right around here at 2 gigayears after the thing is quenched. Well, it turns out it bounces right back onto the main sequence. So what seems to be going on is at least in the enhanced merger run, the presence of a central black hole is not only responsible for making this thing quench, it's also maintaining quenching after it's quenched. So there's a lot of different things going on here, a lot of things to explain. One thing that I want to say straight away is that this is not a straightforward case, it's not a straightforward case of just blasting these galaxies with energy. So I'm going to show you here the total energy injected in feedback in the black hole and supernovae runs as a fraction of the total energy injected just in the supernova-only runs, which, remember, we don't find quenching in those cases. You actually find, if you look at the cumulative energy over time, in all three cases, including the case that quenches very deeply, you're actually injecting less energy in the simulation which has black hole feedback than in the simulation which has only supernova feedback. So in other words, the suppression of the star formation is kind of overcompensating energetically, so that the total amount of energy is just fractionally less when you have black holes present. On the other hand, if you actually take a look at, in the case where we do have black holes, what fraction of that feedback energy is coming from the black hole, as opposed to the supernovae, that's when you begin to see that the black holes are playing a very significant role energetically. So especially in the enhanced merger case, you find that a significant fraction of the total feedback energy has been injected by the black hole rather than by the supernovae. So here's the question, what's going on in terms of why is it that by injecting less energy, you can have a more dramatic effect in terms of switching off star formation? And I'm just going to skip one slide because I'm running out of time. So let's just skip straight to this one. And basically, the upshot is it's not about the total amount of energy you're injecting, it's about how you couple it. And the way you can see this is if you look at the total energy bound up in outflows just outside the main galaxy. So I'm just drawing a sphere here at 10 kiloparsecs and having a look at the total energy in the gas that's crossing that 10 kiloparsec sphere. In the case where you only have supernovae, as the mass of this thing grows, it just becomes dynamically harder and harder to get outflows out. Because the energy is being injected in a very distributed way across the whole gas disk, the temperature you reach and the velocities you reach just aren't high enough to overcome the high potential barrier that you get in a 10 to the 12 solar mass dynamical object. Whereas when you have the black holes, although you're injecting less energy in total, you're injecting it in a much more concentrated way, so you get to higher temperatures and higher velocities, and that means when you're sitting at 10 kiloparsecs, you actually see outflows with enough energy to leave the system entirely. All right, I must skip to my conclusions. So really, the main thing I wanted to show you is we have this technique, genetically modified simulations. It allows us to build controlled tests that sit in a cosmological environment. It's like the best of both controlled simulations and also Zoom simulations for investigating how physics interplays in complex problems like this. We've looked at how the AGN can trigger quenching, but that's kind of enabled by having a major merger. And the other thing that I didn't quite get time to say is that there's no problem in this picture of having AGN coexisting with star formation. So in the suppressed merger case, the AGN is happily accreting away, but it's its effect is enclosed because there's always a dense cold gas disk around it that just stops it from doing anything too dramatic to the galaxy. Okay, I'm out of time. Thank you.
Questions for Andrew, Avishai?
First, I want to congratulate you for doing these experiments. I think it's a great idea to do it and very promising technique. That's exactly the right thing we should do. But two cautionary notes. One, it's not only the AGN feedback which is put in some ad hoc way and we don't really know how to do it right. It's also the supernova feedback, which despite many decades of studies, we still don't know how to really work it out. So this should be judged qualitatively, but of course, what you call AGN feedback may actually go at the expense of supernova feedback and vice versa, and we don't really know. The other one, which is major mergers are not as frequent as quenched galaxies. So this may account for some fraction of the quenching. We may have to think about other quenching mechanisms.
Okay, so let me respond very briefly to both those points. First of all, I completely agree, right? I mean, the subgrid uncertainties are a horrible, horrible problem. And so ideally, you do a study like this and you cut across the subgrid as well as cutting across the merger history, and then you have a full experiment. However, what I will say is one of the nicest things that's being done on this is Ben Keller's work, I think, on this superbubble supernova feedback, where you have an explicit multi-phase model which is regulated by thermal conduction across the blast wave solution. And I mean, he does see that just this thermal conduction process limits the temperature that supernova feedback can get you to. And it's that limiting temperature that in this case is stopping us from launching outflows in massive galaxies. So he has a very nice paper on this, which I kind of encourage everybody to read. On the other point, I've now forgotten what it was. Oh, merger rate, yes. So actually in the paper, we take a look at the merger rate, and we find that at least at high redshift, you kind of can quantitatively account for this. So what's nice about this whole technique, you can do a search for how major a merger do you need to get these effects. It turns out you need a major merger at the level of about 1 to 4 or 1 to 3. And then you can find, well, about a quarter of galaxies have had that at these high redshifts. So it kind of works out, but I agree we need to do more work.
One last question.
In the case of the successful black hole feedback, could you clarify exactly what the physical mechanism is that is either evacuating the gas or preventing it from falling in, or both?
Yes. So this is quite complicated, and there's a lot of discussion of it in the paper. But I mean, the black hole implementation that Michael has put together essentially heats gas. I mean, that's the main mechanism. The argument is that the detailed physical processes are unresolved on these 100 parsec type simulations. So it's simply that you heat a small amount of gas to very high temperatures, around 10 to the 7 Kelvin, 10 to the 8 Kelvin, even in a very small region. And what the major merger then is able to do for you is if it's able to disrupt the cold gas disk mechanically, it kind of makes it susceptible to just being destroyed. But when the disk is just sitting there and merrily forming stars, it's actually very hard to just destroy that cold gas disk just using the AGN feedback. So that, in a nutshell, is what's going on.
Okay. Let's thank you, Andrea, again. Please.